Welcome back to geometry. We want to continue taking a look at section 15, and we want to essentially return to the theorems from section 14, getting the converse of those theorems. So let's take a look at those. So in the previous section, we took a look at the alternate interior angles theorem, and here we're looking at the converse of it. So previously we had, if there we have two lines crossed by a transversal, if the alternate interior angles 1 and 2 were congruent, then the lines were parallel. In this case, what we want to look at is if we have parallel lines, then the measure of this angle and that angle are congruent. So it's the other direction, right? So if we have two pairs, or if we have a pair of parallel lines and they're crossed by a transversal, then each pair of alternate interior angles are congruent. So we start off with two parallel lines with a transversal, and we want to show that this angle, and we'll call it QPY, are congruent. And we'll call it QPY because we're going to find another angle in here. So we want to prove this by contradiction and a two-column proof. So we'll start off with what we're given, two parallel lines, L and M. All right, well, by the Euclidean parallel postulate, M is the only line parallel to L that passes through P. So M is the only line through P parallel to L. And again, that's the Euclidean parallel postulate. Excellent. So let's suppose that we don't have congruent angle measures. Suppose the measure of angle 1, let's actually suppose that the measure of angle 1 is less than the measure of angle QPY. And this is for a contradiction. All right. Our next step then is to recognize that we can find a line that gives us equal angle measure. So there's a point over here, let's call it X, so that this angle, QPX, is congruent to angle 1. So there exists a ray, we'll call it PX, right? PX, such that the measure of angle QPX is equal to the measure of angle 1. Excellent. And that is by the protractor postulate. All right. But what do we have then? Well, whenever we have equal angle measures, then we have parallel lines from our previous section. So we have that PX, the line PX, is parallel to the line L. And that's by the alternate interior angles theorem. Fantastic. But this is a contradiction. Why? Because we have that M is parallel to L and that PX is parallel to L. So this is a contradiction. Lines 2, M being the only line through P parallel to L, and 5, that PX is also parallel to L, so line 2 and 5 contradict one another. M is the only one, but here's another one. So we conclude, let's see here, we suppose this for a contradiction, but again, it doesn't matter that it's less than. We could have put greater than, in which case X would have been out here, or more, a little bit easier to deal with, right? We could have found X to be over here and gone with this angle instead. So it doesn't matter that we choose measure of angle 1 is less than. We could have done measure of angle 1 is greater than, and it would have given us the same collection of lines. So we want to recognize that. Therefore, we can conclude that the measure of angle 1 is equal to the measure of angle QPY. And that's, right, we're saying that's not line 3 because in line 6 we found a contradiction. So this is due to lines 3 and 6. And we're all set. Excellent. All right. So this is just a quick comment that back in section 2, we included the alternate interior angles and its converse together, right? This theorem from section 14 and this. The reason that we don't combine them together is because what we had in section 14, the alternate interior angles theorem, that's absolutely true in any geometry, right? So whether it's the Euclidean geometry or the neutral geometry, which has other geometries, right? That one, the alternate interior angles theorem, is true in all of those geometries. But the converse is only true in Euclidean geometry. So we want them to be separate because they're true in different places. In particular, this one is not true everywhere. So we don't combine them. All right. So much like we had with the alternate interior angles theorem, we have a bunch of resulting corollaries. So the converse of the corresponding angles, all right? The corresponding angles said that if we have corresponding angles that are congruent, then we would have parallel lines. Here, if we have two parallel lines that are crossed by a transversal, then corresponding angles are congruent. Excellent. Right, and similarly to what we did in section 14, you would find that the proof of this can be done using, right, you can give a direct proof from the theorem. Excellent. So the proof is an exercise, make note of this. So corollary 15.5, the converse of the parallel perpendiculars corollary. So 4 lines L, M, and T. If we have that L is parallel to M and that L is perpendicular to T, then we must have that M is also perpendicular to T. The parallel perpendiculars corollary said that if we have 2 lines that are both perpendicular to the same line, then L and M must be parallel to one another. So here we're starting off with them being parallel. Suppose that suppose that one of them is perpendicular, then the other must be as well. Excellent. And then corollary 15.6, the converse of the supplementary interior angles corollary. So in this case, right before we looked at 2 angles. Now let's look at this a little better. 1 and 2, right? We said if these are supplementary to one another, then the 2 lines are parallel. In this case, we want to say that if the 2 lines are parallel, then the sum is going to, or that then the two angles are going to be supplementary. So then each pair of interior angles on the same side of the transversal are supplementary. Excellent. So let me get rid of this picture and we'll use a little bit better one. To do that, I'm going to need to draw some lines. So let's do that in a moment. So let's say I have, oh, I don't want to use that bright green right now though. So let's say I have two lines, L and M, crossed by a transversal. We can call it T, that'd be fine. So L, M, and we can call this transversal T, that would be fine. So we want to show that the sum of two interior angles on the same side of the transversal are supplementary. So let's start off with what we're given, and that's two parallel lines. L is parallel to N. Excellent. That's what we start off with. So the measure of angle 1 is equal to the measure of angle, let's call it 3. We'll show that 1 and 2 are supplementary. So 1 and 3, angle 1 and angle 3 are congruent, so the measure of angle 1 is equal to the measure of angle 3. And that's by the converse of the, watch carefully, alternate interior angles theorem. Alternate interior angles theorem. This is the converse of it. So parallel lines gives us congruent alternate interior angles. All right, well, since we have a linear pair right here, we know that the measure of angle 3 plus the measure of angle 2 is equal to 180 degrees. And that's from the supplementary angles postulate. Supplementary angles postulate. All right, but I can make a substitution here, right? I can replace angle 3 with angle 1, so measure of angle 1 plus the measure of angle 2 is equal to 180 degrees. And that's just the substitution of 2 into 3. And then the last step here, right, once we have this, we know that the two angles are supplementary. Angle 1 and angle 2 are supplementary. And this is, of course, just by the definition of supplementary angles. Excellent. And I believe that is it for this section. Yes, that leaves us with just the exercises. You'll be interested to know here that the parallels postulate isn't the only thing that would land us in Euclidean geometry. There are several different ways that we could actually get there. One of them that they mention here is by saying rectangles exist, because we would find out that rectangles don't exist in other geometries. Another way that we can get there is, let's see, I thought it was mentioned here, but if you assume that the sum of the angles of a triangle are 180 degrees, that would also land you in Euclidean geometry, because that's not necessarily true elsewhere. Okay, so the other geometries that we would look at are or primarily is hyperbolic geometry, is the other one that we'll take a look at. And that we'll get to in section 27 or something like that. It's a bit later. It's in part 3 of the course. So, but that's all that we have for now for this section. So I will see you guys again later in section 16.